All right, welcome to the deep dive. Today we are diving into something pretty fascinating, especially if you're into STEM. So that's science, technology, engineering, and mathematics. We're looking at how spatial training could actually boost success in those fields. And I know you, our listeners, are here because you really want to get smart on this topic, but you want to do it, pretty quickly, right? So that's what we're here for. We're going to cut through all the noise and really get to the heart of what we know about spatial training in STEM.
Exactly. So think of this deep dive as our mission to figure out what the evidence really tells us. Can training our spatial abilities actually make a difference in STEM, whether it's in school or even in careers later on? You sent us a really interesting research article, the 2015 paper by Stephen Uddle.
Right. Yeah. And that's really going to be kind of at the center of everything we talk about today.
Absolutely.
So the million-dollar question, all right? Can we actually train our brains, improve those spatial thinking skills, and then see those improvements reflected in how we perform in STEM and how much we actually enjoy those subjects?
Yeah, and it's definitely an idea that's gaining a lot of traction. There's a lot of buzz around it, so let's dig in and see what the research says.
Okay, so let's rewind a little bit first. Why would we even think that spatial ability and success in STEM are connected in the first place?
Well, when you think about what STEM fields really involve, how you solve problems in those areas, the connection starts to feel pretty intuitive, right? Think about geometry. You're working with shapes, visualizing things, and understanding how they relate to each other in space. Or take geology, you're picturing rock formations, understanding how they've shifted and changed over time. Or even in chemistry, you're imagining these complex molecular structures.
Right.
These are just a few examples, but you see this need for spatial thinking popping up all across STEM. Astronomy, physics, computer science, mechanical engineering, the list goes on.
Yeah. It's kind of feel like common sense in a way, right?
Yeah.
If you're good at picturing things in your mind, rotating them, understanding how they fit together, it just seems natural that you'd have a leg up in subjects that deal with those same kinds of concepts. And I imagine there's research to back that up.
Oh, absolutely. There's actually a decent amount of research now, especially over the past decade or so, showing that there's a moderate correlation between spatial ability and how well students do in STEM. Not just their grades, but even whether they choose to go into STEM careers. And interestingly, there's also some research suggesting that students who score lower on spatial ability tests tend to struggle more in introductory STEM courses. And they actually report enjoying those classes less.
Yeah. Which makes sense, right?
Yeah.
If you're having trouble visualizing something, is going to make it that much harder to learn and engage with the material. And it sounds like this isn't just a correlation we see in school either.
Right. Longitudinal studies, so studies that follow people over time, have shown that people who work in STEM professions actually tend to have higher spatial abilities compared to folks in other fields. And there are a bunch of smaller studies that have found links between spatial ability and success in specific STEM disciplines, whether it's chemistry or various types of engineering or physics. You see these connections pop up again and again.
So we're seeing this consistent link, this relationship between being good at spatial thinking and being good at STEM. And I'm guessing that's led to this whole idea of interventions, right?
Yeah.
If this skill is so important for STEM, then maybe we can find ways to train it.
You got it. There's been a lot of interest, particularly from researchers and educators, in developing spatial training programs that could help students and maybe even adults boost their performance and success in STEM. But it's really important that we don't get ahead of ourselves. Just because two things are related doesn't mean one causes the other.
That's a really important point. Just because we see spatial ability and STEM success going hand in hand doesn't mean that if we improve someone's spatial skills, it will automatically make them better at STEM. You mentioned that there are actually two conditions that would need to be met to make that argument. What are those again?
So the first one is whether spatial ability is even malleable. Can we actually train it and see improvements?
Okay, yeah.
And the second equally important piece is if we can improve spatial ability, does that actually translate into real-world improvements in STEM outcomes? So are we talking about things like better grades, a higher likelihood of getting a STEM degree, or being more successful in a STEM career? Those are the kinds of questions we need answers to.
So two separate but connected questions that we really need to answer.
All right.
Okay, so let's tackle the first one. Can we actually get better at spatial thinking? Can we improve our ability to visualize things in our minds?
Well, on that front, the evidence is pretty promising. There was a really comprehensive meta-analysis. And just to remind everyone, a meta-analysis is basically a study of studies. It looks at the results of a whole bunch of different studies and tries to find overall patterns.
Right.
So this particular meta-analysis looked at over 200 studies, and it found that spatial training does lead to improvements in spatial ability. And the average improvement was pretty substantial, almost half a standard deviation.
Almost half a standard deviation. That's a pretty noticeable change, right, for those of us who aren't statisticians.
Yeah, in the research world, that's considered a meaningful difference. And it wasn't just one specific type of training that showed these effects either. The studies included in the meta-analysis used a wide variety of training approaches.
Oh, interesting. Like what kinds of things?
So some were formal spatial training programs, some were just the spatial reasoning skills you naturally build up by taking STEM courses. Some involved playing video games that have a strong spatial component, and believe it or not, some even looked at things like dress design because that requires you to visualize how different pieces of fabric will fit together.
Wow.
And what was also encouraging was that some studies showed that the benefits of training could last over time. And in some cases, they even transferred to different types of spatial tasks. So it wasn't just that people got better at the specific thing they trained on, but it actually seemed to help their overall spatial reasoning abilities. Now, the researchers did identify some factors that could influence how effective the training was, things like how the control groups were chosen. But overall, the evidence suggests that we can indeed get better at spatial thinking with practice.
Okay, so that first link in our chain, the idea that spatial ability can actually be improved, that seems pretty solid. But now for the really big question. Does improving spatial thinking actually lead to better performance in STEM? And I'm guessing this is where things get a little bit more complicated, right?
You're exactly right. While we have a lot of evidence that spatial ability is trainable, there actually aren't that many studies that have directly investigated whether improving those skills actually makes a difference in STEM outcomes. In fact, if you look at the past 30 years, there have only been a handful of studies that were designed to specifically answer that question.
Wow, a handful. That's pretty surprising. So what did those studies actually find? Let's break down those results.
So one of the earlier studies was done back in 1983, and it looked at chemistry students. The researchers used a program that focused on model-based reasoning. So they had the students working with molecular models, trying to connect those spatial representations with the concepts they were learning in chemistry. And they did find a small improvement, around 3 percentage points on some of the assessments they gave the students. But there was no real difference in their overall course grades. And one of the limitations of this study was that they didn't actually measure whether the students' spatial ability improved as a result of the program. They also didn't control for other cognitive abilities like working memory or reasoning skills that could have also contributed to those small gains. So it's hard to say for sure whether the program itself was really what caused the improvements.
So some hints of a possible effect, but not a clear-cut answer. What about other studies?
Another study, this one from the late 90s, looked at engineering students. They had a voluntary workshop where students would go once a week and work with Duplo blocks. You know those big Lego blocks that little kids play with?
Yeah.
So the students were using those blocks to build models and practice creating and interpreting orthographic projections, basically different 2D views of 3D objects. And what was really interesting was that while they didn't find an overall improvement in the students' spatial abilities as measured by standard tests, they did find that the gender differences in spatial ability that you typically see with males often scoring higher or well, those differences actually disappeared by the end of the course. Now, this study had some limitations in terms of its design, so it's hard to draw strong conclusions about whether the workshop directly impacted the students' achievement in the engineering course. But the researchers did note that none of the students who participated in the workshop actually failed the course that semester, which was an improvement compared to previous semesters.
That is interesting.
And since then, there have been some important studies that have tried to build on these early findings and really nail down whether spatial training can impact STEM outcomes. And one researcher who's done a lot of work in this area is Cheryl Sorby. She's done a lot of research specifically with engineering students.
Yeah, I've come across her work before. It seems like she's been a real pioneer in this field.
Absolutely. So over more than a decade, she actually developed a full-fledged spatial training course that lasts 10 weeks. And it's specifically designed for students who enter engineering programs with lower spatial abilities. Her curriculum includes lots of hands-on activities, things like paper folding, drawing orthographic projections, remember those from the Duplo block study?
Right.
And also tasks where students have to visualize rotations and cross-sections of different objects. So lots of different ways to really engage their spatial thinking.
And I recall that the results of her research have been pretty positive, right?
Yeah, they have. Her earlier studies found that students who took her course not only improved their spatial abilities, which is what we'd expect, but they also got better grades in their engineering courses and even had higher overall GPAs. And what's important is that these studies did suggest a link between those improved spatial skills and the better academic performance. And then more recently, she and her team did another study where they used a more rigorous design called regression discontinuity. I won't go into all the details, but basically, this method helps to account for the fact that students who choose to participate in a training program might already be more motivated or have some other advantages that could explain why they do better.
Okay.
And even with this more rigorous design, they found that students with low spatial skills who took the training course ended up performing better than you would have predicted based on their initial skills. They even outperformed some of the students who had higher spatial skills but didn't take the training. And they even saw some small improvements in calculus grades. So, those results are pretty compelling.
That does sound promising. But I do remember that in her studies, the effect on grades was noted as being small, and that spatial ability only explained a very small amount of the difference in grades between students.
That's a really important point to keep in mind. Even though our findings are positive, the impact of the training on grades was still relatively modest. It suggests that spatial ability is definitely one factor in academic success, but it's certainly not the whole story. There are clearly other things that contribute to a student's overall performance.
Right. Makes sense. Okay, so some encouraging findings in engineering. What about other STEM fields? You mentioned a study that looked at physics.
Yes, this study involved college students taking physics, and they added a supplemental workshop that was based on Sorby's curriculum, so very hands-on, spatial reasoning tasks. And like the engineering studies, they found that the students who went through the workshop significantly improved their spatial abilities, which isn't too surprising. And they also found a small positive effect on the students' grades in their physics course, specifically on tests that covered Newtonian mechanics. But here's the catch. When they followed up with the students 6 months later, those gains in both spatial ability and physics achievement had basically disappeared.
Oh, wow. So the effects weren't lasting.
Right. And that's a really important consideration. If the benefits of spatial training fade away so quickly, it raises questions about how practically useful it is in the long run.
Yeah, definitely something to think about. Now,
Yeah.
you also mentioned one more study that I thought was particularly interesting because it involved younger children.
Yes. This one focused on math performance in early elementary school. They had kids between 6 and 8 years old, and they compared a group that got spatial training. They used a mental rotation task, which is where you have to imagine rotating a 3D object in your mind. They compared that group to a control group that did crossword puzzles. And what they found was that the kids who did the spatial training actually got better at solving addition and subtraction problems, particularly problems where there's a missing term, like, 2 plus blank equals 6. The researchers think that the spatial training might have helped the kids to visualize the relationships between numbers and to mentally perform the transformations needed to solve those kinds of problems. And the kids who did the crossword puzzles, they didn't show the same improvement.
That is fascinating. It suggests that spatial reasoning might play a role in math even when it doesn't seem obviously spatial.
Exactly. And it really highlights how intertwined these different cognitive skills can be. Okay, so we've covered a lot of ground here, looking at several different studies. What's the overall conclusion we can draw about whether spatial training can actually improve STEM outcomes?
Right, so we've talked about the promise of spatial training, we've looked at the evidence, and now it's time to sort of synthesize it all, right?
Exactly. And I think it's fair to say that based on the research we've discussed, the evidence only partially supports the claim that spatial training leads to big improvements in STEM achievement. So while there's clear evidence that we can train those spatial skills and see improvement, the actual impact on STEM scores across all these different studies has generally been pretty small. And we don't yet have any convincing evidence to say that spatial training leads to more people choosing STEM careers.
But I think it's also important to remember that the positive effects we did see, even if they were small, often occurred in real-world classroom settings where there are tons of other things going on that could influence a student's learning.
Absolutely. The fact that we're seeing these positive effects, even within those complex learning environments, does suggest that there's potential there. There's something worth exploring further.
So what are the next steps then? How do we get more definitive answers about whether spatial training is really a valuable tool for boosting STEM outcomes?
Well, most researchers agree that we need more research, but it needs to be even more rigorous, more carefully designed than what we've seen in the past. The good news is that none of the studies have found that spatial training is harmful or less effective than just teaching things the standard way. So we're not doing any damage by exploring these interventions. But to really establish that causal link, that training spatial skills actually causes improvements in STEM, we need studies that use strong designs like randomized controlled trials. That's where you randomly assign students to either get the spatial training or not, and then you compare their outcomes.
Okay.
And we also need to be much more careful about accounting for any pre-existing differences between the groups of students we're comparing. For instance, if students who are already more motivated are the ones who volunteer for spatial training, that could skew the results.
Right. It's not just about showing that it works. It's about understanding how and why it works.
Exactly. We need to include measures of other cognitive abilities, not just spatial skills, so that we can really isolate the specific impact of the training. We want to be able to say with confidence that any improvements we see in STEM outcomes are actually due to the improvements in spatial ability, and not just because the students got better at reasoning or remembering things in general.
Yeah.
And remember that study by C and colleagues where they saw improvements in achievement without any corresponding gains in measured spatial ability? That just highlights how important it is to really dissect what's going on.
Absolutely. And it's not enough to just do these studies in a lab setting, right? We need to see how these interventions actually play out in real classrooms.
100%. While lab studies are definitely important for tightly controlling things and figuring out the basic mechanisms, we need more research that takes place in authentic learning environments to make sure that the findings are relevant and applicable to real-world teaching. Now, these kinds of studies can be tricky logistically, but they're definitely doable. There are some great examples from other areas of educational research where they've been able to do this effectively. And when it's not possible to randomly assign students to groups, which is often the case in schools, we can use techniques like matching to create control groups that are as similar as possible to the groups getting the intervention.
You also mentioned something about the potential for using learning analytics in this research, right?
Yes, I think that's a really exciting avenue. Learning analytics is basically about using data to understand how students are learning. So we can look at things like how often students are engaging with online materials, what kinds of questions they're asking, how they're interacting with their classmates, and even their patterns of eye movement as they're reading text or solving problems. And by combining that kind of data with measures of spatial ability and whether students have received spatial training, we can start to uncover really detailed insights into how these interventions might be working differently for different students.
That is fascinating. So as we wrap up here, what are some of the key things that researchers should be keeping in mind as they move forward with this work? What are the big questions that still need to be answered?
Well, one thing to remember is that spatial training often leads to improvements on very specific types of spatial tasks. So if we're not measuring those same skills in our assessments of STEM achievement, we might not see a big overall improvement in grades or performance. It's like if you're training for a marathon by only doing sprints, you'll get faster at sprinting, but that doesn't necessarily mean you'll be able to run a marathon.
Right. That's a great analogy. What else?
Another big question is about critical windows of opportunity. It's possible that there are certain times in development or in a student's educational path when spatial training might be most effective. Like maybe it's more beneficial to do it before students even start taking STEM courses, or maybe during those early introductory courses when they're first grappling with those core concepts. We know that the relationship between spatial ability and things like math performance can change with age. And there's some evidence suggesting that spatial ability might act as a kind of gatekeeper early on in STEM, meaning that if you don't have those skills, it might make it harder to progress in those fields.
Interesting. So the timing of when we provide the training might be really crucial.
Exactly. We also need to figure out whether the somewhat limited effects we've seen so far are simply because the training hasn't been long enough. Maybe we need to have students engage in these spatial tasks over a longer period of time to see more lasting and robust improvements. And related to that, we need to understand when we can expect to see those benefits. Is it immediately after the training? Or maybe it takes time for those improvements to show up in things like grades or career choices.
So much to still explore. All right, so as we bring our deep dive to a close, what's the key takeaway for our listeners today?
I think the main message is that while the idea of using spatial training to boost STEM success is really exciting and the early research definitely shows promise, we're not quite there yet in terms of having rock-solid evidence that it works consistently and powerfully. We need more research, and it needs to be really high-quality research to give us a definitive answer about how big the effect is and how long it lasts.
So no need to rush out and start implementing widespread spatial training programs just yet.
Right. I think it would be premature to do that based on what we know right now. But that doesn't mean we should abandon the idea. It's definitely worth continuing to explore, especially with a focus on understanding exactly how it works. And one thing to always keep in mind is that improving success in STEM is a really complex challenge. It's not a one size fits all situation. Spatial ability is just one piece of the puzzle. Students face all sorts of difficulties in STEM, from understanding the content to managing their emotions to feeling like they belong in those fields.
Right.
And spatial ability is just one factor that might be contributing to those struggles. But even if the effects of spatial training are relatively small, they could still make a real difference for individuals who might otherwise be excluded from STEM or who might not reach their full potential in those areas.
That's a great point. Even small improvements can be meaningful, especially when we're talking about something as important as STEM education and careers. So despite the unanswered questions, this is still a field with a lot of potential. And I think your overview has been incredibly insightful. So with that, here's a final thought for our listeners. If spatial skills are so important across so many different areas of STEM, what other cognitive skills might be similarly untapped? What other abilities could we be training to help people learn and achieve their goals, not just in STEM, but in all sorts of fields? It's an invitation to think more broadly about the power of cognitive training and its potential to unlock human potential in all sorts of ways. Thanks for joining us for this deep dive.